analysis, what it is. But then I also like to introduce, of course, our software. We have a special version of ARTeMIS Modal that we call ARTeMIS Modal EMA. And it's simply a version where we have, you could say, only the features that are applicable for experimental modal analysis included in this version here. So it's a special license that is of this software. And this is what I like to show today, what you can get out of this particular version of ARTeMIS. If you have any questions, there is a question and answer QA function in Teams that you can hit, and then there is up in the top bar, and there you can then write some questions, and then we will try to answer them. Maybe some of them will be answered while we are talking, or I'm talking, by some of my colleagues, and otherwise we will try to respond after this webinar here. And otherwise you can also email us with your questions to this email address, info@sweeps.com. But this is the idea for the next hour or so. We're going to talk about this. So an introduction to modal analysis. Let's do it a little simple, but you can consider some kind of simple structure. That is it could be a pole, or it could be, I don't know what, chimney or something that is standing out, being subjected to some forces that cause it to vibrate. What you get out of that is that the structure will vibrate with a mix of all the different dynamic modes that is excited by the excitation that is provided. So this is actually, you could say, what we are looking at when we are looking into the physical domain, when we are measuring things. But what we do in modal analysis is we try to make a little systematic, try to find the different building blocks that together form, say, the dynamic performance of this structure here. So what we get out of that when we do modal analysis is we first of all get a mode shape for each of the dynamic modes. So there will be different ones, the first and second and third order and so on of modes. And together with these, there are some parameters that also describes the way the structure behaves in this particular dynamic mode. And these parameters are the natural frequency that tells you something about how fast this particular mode likes to vibrate at the resonance frequency. It also tells you something about how fast it can die out, this particular mode of vibration, if you hit it and then you let it die out. The parameter that describes this is called the damping ratio. And then finally the mode shape, as we already have this introduced here. When we do experimental modal analysis, we are measuring both input and output. And this allows us also to get another parameter that you will not get if you did operational modal analysis, where you only are treating or analyzing the responses. In experimental modal analysis, you can actually get the actual scaling of the different modes compared to one another. And this can, for example, be expressed in terms of the modal mass. So this is an additional thing that you can get from doing an experiment where you measure both input and output. Let's see here. The framework, or the idea behind, you could say, experimental modal analysis is that we have some kind of structure symbolized with this blue box here. This structure here we would like to test and then find out what are the modes, how are they looking for this particular structure here. So what we have to do is, first of all, we have to make some assumptions. The first assumption we have to do is we have to assume that this structure here we are testing here is vibrating or having most of vibration that are not changing with, let's say, the level of excitation. So that means if you have a weak excitation causing a weak response, the modes that are causing this are exactly the same as if you have significant higher excitation that gives you a higher response. That's linearity. That means that the things are exactly the same seen from a dynamic point of view of this structure here. And this is what we actually are assuming when we are doing this type of modal analysis. Another thing we have to assume is also that this structure here is not changing its dynamic behavior throughout this test we are going to do. I mean, if it's a big structure, experimental modal analysis test might take hours. Whereas if it's a small one, it can take a few minutes and then that's it. But you can imagine if you have a large structure and this structure here for some reason maybe changes its temperature or other things, then this structure here will change its way, its dynamic way of behaving. If it heats up, you get another stiffness than if it's cooled down. And that means that when you have another stiffness, you also get another natural frequency and so on. So it's really important that the conditions are the same throughout the test you're doing. Otherwise, things will be messed up inside the analysis and you will get some kind of average of what's going on in this case here. So make sure that you are in an environment where you get, you would say, the conditions to be the same throughout the whole test. Another thing that is really important when we do experimental modal analysis, that is, in fact, that the excitation that we are supplying that causes vibration and response measurements, we have to be able to measure everything that is actually going on in this structure here. It also means that if you have something that is also affecting this structure here while you're doing the test, but you're not measuring what causes this vibration, or you're not measuring this vibration here or this excitation, then this will actually pollute your measurements. There will be some unknown input forces mixed together with the known measured. And this is not good. It will be terrible for you, the results that we get out, if we have this kind of mix. So it's really important that the structure is isolated in some way, so that the thing that you supply of excitation are the ones that actually are being measured, all of them, and used. And one thing that I am noting down here is that ARTeMIS Modal EMA relies on frequency response functions, which is what we are trying to get from this type of measurements here. We are measuring the response the structure is doing to some measured excitation. So you can imagine we have response and we have excitation in time domain. We will now turn this into frequency domain by some processing. And then we can divide these two things with one another, and then we actually get a transfer function between input and output. And in experimental modal analysis, this transfer function is called the frequency response function. I'll come back to it a little bit later, how we actually do it. But the FRFs, or frequency response functions, these are the basic functions that are used for the modal analysis tools we have in ARTeMIS. So this is what we are aiming for here. How can we get these in some way? Let's look at that. Again, a little schematically, how do we actually do it? If we're doing something we call impact testing, which is a very typical way of testing smaller structures, then you can imagine we have a structure that we have mounted in some test rig so that it's isolated from everything else. We will then place one or more accelerometers that can measure the response in some points. And then we will use this type of impact hammer here that has a kind of a little force transducer sitting out here in the tip. And then when we hit with this force transducer here, we can now measure then the input force that we have supplied. So when we look at this, when we hit this one here, this structure here, the structure will respond with some kind of free decay function. It will die out after a while, but it will start behaving like this because there are some memory inside this structure here. The damping is then damping out you could say the vibration, but it will keep ringing, you could say, for a while, this structure here in this measurement point that we have here. At the same time, we have measured the inputs, and the input will just be a spike like this, where the input force is applied, and after that, nothing happens in this signal here. It will be more or less zero. What happens then is we take this, these two signals here, we take them from time domain to frequency domain, and we do that by something called a fast Fourier transformation that allows us to calculate a spectrum of the response. That will look something like this with all the peaks of the different modes of vibration. And then another spectrum down here that is the input spectrum. And this is typically a more or less flat spectrum. The more flat, the better. And this is, you could say, close to what we would call a white noise excitation. If it's completely flat, it's completely white noise. But normally you'll see that it has a kind of it dies out a little bit in the higher frequencies, but still very flat, exciting all the different frequencies in this range that we're looking at. These two here we can in different ways divide with one another. So we divide the response with the input. And then what we get out of that is we get this function here we call the frequency response function, which is a nice clean function because you have divided the input out of the output. And what you are left with is actually only information about the actual system that we are testing. And this is, of course, assuming that you have measured all inputs and also output, of course. If there are inputs that are not measured but coming in through the test here, this function here will be polluted because you are not dividing all the output out of the input. So it's really, really important that we isolate the structure and we make sure that everything that is affecting it is measured, all the different excitation. This is what we need for analysis in ARTeMIS Modal. There are other tools available that actually operates on the equivalent time domain, you would say function. This is called the impulse function, impulse response function. But we are dealing with the frequency response functions in ARTeMIS. So this is the idea, what it is that we are trying to do when we are either loading data files in or we are doing impact testing inside the software. There are two different ways, in principle, that we can do things. One is we can fix, you would say, the output. So we can fix some accelerometers somewhere on our structure. And then we can move around with the input, which could be a hammer or it could be a shaker we are moving around with. And then all the different points where we are making inputs are then the places we would like to know the most shape in a case like that. If you do that, then we get, you could say, we get rows in the frequency response matrix. The frequency response matrix is per frequency the different relations we have between the different inputs and the different outputs. So the columns we have, entries we have in this matrix here, this is the inputs. And the rows we have are the outputs. So if you have a single accelerometer sitting here, and you are having a lot of different impact positions here that you are doing impacting in, you will have one row like this and many column entries. But there will only be a single row for a single accelerometer output. If you have two accelerometer outputs, you will have two of these rows. So the more accelerometer outputs you have, the more rows you will get in this case here. You can also do the exact opposite. You can try to fix the input to a specific location. And then move around with your accelerometers in different locations, or just place a lot of accelerometers at different locations at the same time. But now you have a single input and multiple outputs, and now you will get actually one column, as you can see here, with the entries of rows, entries here, because you have many responses, many accelerometer positions, but only a single input position here for the shaker. If you have two shakers, then you will have two columns, three shakers, three, and so on. So you can see you will not get the full matrix normally in either of these two ways of testing. But it turns out you don't really need that. You can actually live with much less information, which is what we normally will do. Today I will try to show you how we do this in ARTeMIS, the impact testing here with an impact hammer. There are three different ways we can get FRFs into ARTeMIS. And I will try to show you now a little quickly, perhaps two of them, and then go into the more details with the impact testing. But there are the normal way that ARTeMIS always have been working and by birth designed has been that you import measurements from files, and then you process them inside, and then you get whatever you could say functions you need in order to be able to estimate your modal parameters. So we have different ways we can import, you would say, information for experimental modal analysis. There are the ones that one of them is that we import time series data. So you can imagine that you have been measuring, either you have had a shaker shaking the structure for a long time, and now you have a long recording of the input and the response of them. You can actually import it in and then use ARTeMIS to produce the FRF then from this time data. You can also have impact testing, where the different impacts are stored one after each other in the files for a particular place of your sensors and impact positions. And then you can import all this and then do FRF estimation inside ARTeMIS. So this is one of the ways you can do it. The other way you can do it from files is that if you have already the FRFs stored in files from some third-party software, then you can actually import them together with a geometry, if you have that available also, into the workspace, and then very easily then get started with the modal analysis. So that these two different ways that you can actually work with files. And then finally there is the impact testing module. But let's just see the two others here, how they work. The first one here is where we use our really good old way of getting data into ARTeMIS and create a project. That's through this configuration file. That was the initial way we did it, I don't know, 28 years ago or something now, when we started developing ARTeMIS. And we still have this one here, and it's still widely used as a way. And I can try to show you here. Let's see if I have some data here. What we need here is, you could say, we need a configuration file that is a text file. I can try to open this one here. This file here is one where you put in information that is needed in order to create the geometry, specify what sampling interval has been used, specify how many measurement files and what measurement files you should use, and also where the different measurement points are. So all this comes into this specific project file here, or configuration file. So you can see it's driven by some keywords that you put in. There is a header, that's just a title you put. Capital T is the sampling interval in seconds. Nodes, this is the geometry nodes, the test geometry that you define. First item here, let's see here. This item here, this is the node number that you can define. And then you have X, Y, and Z coordinate of this particular node here. So you can define all the nodes that you need in order to create a test geometry. That should be a simple geometry that matches the geometry, but in a simple way. We never recommend that you import a big AutoCAD file or something, because you will have a lot of nodes that you don't know what to do about because they have not been measured. So make sure to make a simple test geometry in general. Below here there is a section here defined with this keyword lines, and this just tells ARTeMIS that you want to have a line, trace line, drawn between two nodes here, 4 and 10, and then it will make a line there. And then you can make as many of these trace lines as you want, as you can see here. Then you have surfaces. It's exactly the same. You can link 3 nodes with a solid looking triangle, and then if you put enough of them, then the whole thing will look very solid. And this way here you can then define a solid looking test geometry, and this is what we do here by these many surfaces here. More interesting is perhaps that we come to this section here that is called setups. In setups, this is the keyword. We define one measurement like this. So this is the first measurement, the first test setup we have been doing. We have been storing 3 channels of data for this particular setup. In this case here, the first channel here is located in node number 12 in a direction 0, -1, 0. So that's -y. And other things that are important here is that it's in Newton and it's a force channel like this. The next 2 channels are also located in the same node, but this is acceleration channels that are measured in G, as we can see. So this is important information because this allows ARTeMIS to figure out if it's force, it knows it's an input channel. If it's acceleration, it knows it's a response channel. So we don't need to specify that further, but only like this. You have to do this for each of the different impact locations or shaking locations you have been doing. Then you have to you store a file and then get it in like this. So the next measurement is this one here. That's another file, as we can see here. Another locations for the impact position. This is now node number 11, as we can see. And in this way, this carries on until the test is complete, as we can see in the bottom here. If I open ARTeMIS, I can try to open ARTeMIS Modal and then load this. Let's see if I can find ARTeMIS here. It is here. So let me just see if I can. If I drag this one here, this CFD file, you can just drag it in here. Now it will load, and it has automatically figured out that there is actually input channels, so it's okay for ARTeMIS Modal EMA. It's going to be a project for experimental modal analysis in this case. Now, the ones of you that might have seen ARTeMIS before will look at this and say that this looks like operational modal analysis. It's more or less the same we have to do. We have to process the data, and then after that we can do a modal analysis. What we need now is not to process it to get whatever we need for operational modal analysis. Now we need to process to obtain FRFs. So we can start having a look at the data. We can go to manage measurements here. Here you can see that this first setup here has 3 impacts that are just stored one after the other. So it will make sense to load or make 3 segments of data and then average those to get, you say, the specters, and after that the FRFs. So let's go back here to prepare data. I will go down here to spectral density estimation here. First of all, we had these distinct impacts, or free decay functions and impacts we saw in the file, which means that we'll just grab one section at a time and process it. We will not make any kind of overlap between these, because that will not really make sense in this case here. So what I'll do is I will delete, or I will zero out any overlap. So I'll take one segment and then take the next segment and then the next, like this. And then I want to have only 3 averages, because then I know I have taken the 3 impacts I have, and I can do that by increasing resolution to 2048. Then we can see we have now 3 averages available. So that means that ARTeMIS will now load 1/3 of the file and make an FFT, make a spectrum, and then load the next one, do exactly the same, and then average these spectra together before we start calculating the FRF. Let's go down here. The next we have to do is we have to look into what type of response is it. We have, well, it was free decay functions, transient data, you could say. So using a Hanning window that is designed for stochastic data is not really suitable. We saw also that it damped really nice out to 0 in the end, so we don't really need any window in this case here. Not for this data. It could be for the data we will have to do it. We will see that later. And the same for the force. Here we can also select none, but we can also introduce, if you want, a force window that will kill everything after the actual peak. But let's just do it simple and then not select anything. And then down here we can then select what estimator to use. And there are different ones available in our software. We have the H1 and H2 and then H3. And this is a matter of where you believe that the noise is most heavy. Is it on the response or is it on the input? In this case here, we just choose H1. And then we press the process button that actually then processes the data and produces the FRFs. And from the FRFs, we then get our complex mode indicator function, as you can see here. We can also have a look at the FRFs. We can just click up here, and then we get all the different FRFs that are available shown here. We have 2 outputs. We have all these inputs here. So I can just I can select one of them. It shows up here. You can then change how you want to look at this. If it's this is magnitude, you can also have real and imaginary, and so on. We can also, in this case here, because we have processed the data, we also have coherence available then, which allows us to see how much correlation there is between input and output. And again, we can try to select the same one here, and we can see now the coherence here below, which should, of course, be 1 in the areas where we have our different modes, or in between the modes, and then this looks quite nice here. So this is functions we can get because we have processed the data. This is how far I want to go with the data for this one here, because we are going to look at the analysis later. But imagine that we are ready now, we have the FRFs, we can just jump now to mode analysis and then do that if you want. Let's go to the other way we can do it. I will just go to the presentation first, I think. Now, where is that? That is here. This is a universal file format. This one here is you could say an import facility we have made, because universal file format is a little special. It's used by many different software packages for, you could say, transfer of data between different software packages. And of course, we support this also. So what you can get out of this is you can do a test with some other measurement system. That can be a LMS system, or it can be a BNK system, or DevSoft, or whatever they call all of them. And then you can export FRFs that are produced there together with the test geometry that you made there. And then you can actually import all of this into ARTeMIS and continue to try to use our analysis tools on the same data. So this is how or why this has been designed, this import facility here. And we can try again just to see how it looks. I will have to go to ARTeMIS again. I have it here. So now I will delete or close this project here. And then I will make a new project. So now I will try to go here to new project. And now I can try to go here to UFF. That is this particular setting that allows us to import a project that already has been created by someone else. There are 2 things we need to import. We need to import the test geometry, and then we need to import the functions that are created. And in this case here, it is the frequency response functions that are going to be imported. So what I have to do is I have to find this data here, and I have it lying here in this folder here. Let me see. Here I have one file here. This file here contains some universal file format data sets that allows me to define a geometry, test geometry. The first one here, number 15 here, this is nodes. Next one is trace lines, and then we use this one 2412 for surfaces. So having these three here, you can then create a geometry. We also support there are many other ways that you can actually define a geometry in a universal file format, and we support, I would say, most of them at least. There might be some that I have not seen yet, but there are many different other data sets that can be used to define a geometry, and we can also load these. There is another file here, similar looking. It's a text file, as we can see. It starts with showing here the data set number. This is 58. 58 is the place where you store, you would say, measurements or functions that you are transferring from one software to another. And in this case here, it is the FRF that has been transferred. And it looks like this. There are a lot of these data sets, one by another, below this in each other in this file here. And together, when we load it, then we get all the different FRFs that have been measured and exported. So this is what we need now to find. If I go here to load this one here, this is the one I have here. This was the geometry file. And then I can go here and I can load the FRFs in this section here. There can be many files with FRF because some softwares, they store it per, you say, setup. So when you impact one place, you get all the FRFs for that particular impact position in one file, and then if you impact another place, it will be another file. So if you have that, then you can just click this plus button here and then make a multiple selection. So you get the whole list of different files that needs to be imported. Then you click finish when you have done all of that. And you then get this list here that allows you then to look through and see, is this only FRFs I have here, or do I have other types of functions that I don't need in this project here? If there's something here that you don't need, you can always deselect it before you import it. But here it's just FRFs, all of it. So I simply click this button here called Import All. And now I have a project like when I finished the signal processing in the previous project. Everything has actually now been processed. FRFs are available, and we can actually start now doing the mode analysis. One thing to mention is that you can see now there is no coherence available, only FRFs and is the CMIF that has been derived from or estimated from the FRFs. Because in this case here, we had only FRFs to import, so we have no way of constructing the coherence in this way here. So it's not available in this project here, unfortunately. So whatever is loaded and can be used for EMA will be located as under this frequency response section here as functions that you can view if you want to study what's going on before you do the mode analysis. This is how you can do it when it comes to importing universal file format. I will see if I can find my presentation, and then we will go to the impact testing part, because this is the third way you can do it. That is that you can create a project. You can link up with some hardware, some data acquisition hardware that is connected to your computer, and that we hopefully inside ARTeMIS are able to communicate with. There are different types of vendors that we currently support. It is a growing list as we get, you would say, requests. But for now, we have these 4 different types here. I'm going to use this national instruments here, but I can try to see, I have, just for you to see what it is that we otherwise have, the CMIF mesh technique. They have this kind of boxes here called Apollo. They have them with more channels than this one here, but this is a typical one from CMIF mesh technique. We also have from HBM, we support these Quantum X units here. This is a 4-channel unit, but you can get them in 8 and 16 channels also if you want. So these are supported also, and my idea is actually I will make some special YouTube videos in the coming weeks where I will try to show how can you actually connect to these different types of hardware, because some of them are a little bit more funny to connect to than others and operate. So we will try to do that in order to help the ones of you that are working with a specific type of hardware. But for today, I will use national instruments for this test here. So one thing that is worth mentioning is for this type of internal impact testing we do, what we need to do is we need to create a test geometry or import it. And then, of course, we need to produce the FRFs by means of impact testing, in this case here. To do that, we need to connect to some hardware, and to do that, one will need an additional license on top of ARTeMIS Modal EMA. What you have seen so far, uploading files, only require ARTeMIS Modal EMA license. But if you want to connect to some hardware, some of these 4 types of hardware, you need an additional license that opens up for this part here of the software, so you can actually now talk with the hardware. So that's our data acquisition plugins that I'm mentioning here, and there are 4 different ones to choose among. There are different ways we can do it when we come to the actual test. By default, we are doing something we call fixed output rowing input. And that means that we are placing 1 or more accelerometers in fixed positions. And now we are using the hammer, and then we are moving around with it. So we are rowing around on the structure like this. This is the first type. You can also do the opposite, because sometimes maybe it's very difficult for you to actually impact all of the locations. It can be very narrow, perhaps between parts of the structure. So it can be difficult to actually have the hammer there. So you can actually do the opposite. So you can mount sensors in the locations where you like to know the most shape, and then just impact 1 or 2 points every time you move around with the sensor, the accelerometers, and then you impact again the same place. This is what we call rowing output and fixed input. And then there is also the mix. It's a little bit more tricky to work with, perhaps, but you can actually also move around with your input and output. But it's a little, you have to be a little bit careful. So you cover all the different, you would say, combinations of input and output that you will have in your frequency response matrix. But this is something I have shown in a previous webinar, so I'm not going to dive into that today. But this is what we are going to do. And I'm going to use this structure here. This is, we call it a Jim beam. Structure. It's of aluminium. It has 2 plates that are of this size here. So it's 30 centimeters by 10 centimeters, and then there is a smaller one connecting them here. That is 15 times 10. And then they are bolted together in the bottom here. I'm going to fix 2 accelerometers up here. One that is measuring in one direction, and then another one in the perpendicular direction here. And now the idea is, of course, to use the impact hammer to impact the different locations here, as we can see here. I'll try to see if I can connect. I have a camera that is pointing to this structure here. Let me just see if I can get this running here. That was not the right one. We can take the next one. So here we are. I hope you can see it. It's standing here next to me on a small table. And you can see again the same that we have our 2 accelerometers here that are sitting here. we have our data acquisition system here. We have channel number 1. This is our impact hammer here that is connected to that one. Channel number 2, that's the accelerometer we have here that is going this direction here of when it measures. And then channel number 3 is the one that is going in this other direction here. So there are these 3 channels in use of this data acquisition system here. Let's try and start the software up and then see what we can get. And of course, I could spend a long time to prepare a geometry for you, and I chose not to do that because otherwise I think we would be standing here for more than 1 hour. So what I did was I have prepared a project that, see if I can find it here. Hang on. I have already prepared some part of this project here. So that means I have created this, geometry, and I have also already assigned the different positions where I want to have, you say, the impacts. And you can see here, if we take the first one here, the one I've selected here, this is the impact I have here in this direction. I then have, this is the accelerometer number 1, you could say here. And then I have the other accelerometer sitting in this direction here. So I have done this. I have to, we call it replicate. I start defining this one here, and then I actually copy this. I make a copy of this 15 times more because I need 16 setups in total. So I have done that, and then I had to drag it out to all these different locations, and I did not want to tire any of us with all that. So it's already prepared, as you can see. So what we have to do now is we have to go to the actual impact testing part. And you can see we have here 4 different hardware options. And the one that is now connected to this computer here is the National Instruments hardware. What we can do now is we have to, what we do is when we start up this task here, ARTeMIS will try to ask the data acquisition hardware what it has of sensors. All the sensors that are of a type with a TETS information, that means it has this built-in calibration, they can automatically be read and configured. And you can see this is the case for the 2 accelerometers. They are already green here, showing that they actually have been identified, and we have read all the calibration information, so everything is good there. When it comes to the impact hammer, we do not have TETS information available there, so we have to actually tell that it's a force transducer. And I already have put in some calibration information that I can read on the calibration sheet of this hammer here, and then put into an XML file. This is the, if I click here on the sensors, I'm allowed then to say create and edit this XML file that is stored locally on the computer here. And in this one here, I already have put information about this impact hammer here. So I can just select that. So that means the first time you have to configure, you have to type in all that stuff in a dialog, this sensor dialog here. But then you have it saved in this sensor definitions file, XML file on the computer. If you now need to install ARTeMIS on another computer and use it there, you just grab that XML file also and you copy to the other computer, and then all the calibration information is also remembered there. So that's quite convenient. So we click OK. And now we just have to confirm, and that's just, you know, if we have been spending a lot of time here and then accidentally we click this OK button here, it would be terrible because then we would have to start all over again. So here we just get this "Are you sure?" dialog type, and we say yes, we are sure that everything is configured as it should be. Now we can come to the impact testing part of the software. And here the first thing we have to do is we have to tell how does you say the channels inside ARTeMIS. We have defined the first channel to be input, and then the next two are outputs. How are they matching the hardware? I mean, the hardware channels, they could be located in other ways. I don't know why, but they could be. So you have to tell that the software channels, you could say, from your project, how are they related to the physical hardware channels we have on our data acquisition system. In our case, we have connected hammer on the first channel and then the two accelerometers on the next channels. So there is a one-to-one match between what we have done in our projects and what we have physically on our data acquisition system. That makes it very easy because I can click this auto assign button here that just tells the software that how these things are linked together. And you can see now everything lights up in green here. That means that we have identified the different channels and how they should be matched with the ones in the project. We can also load a little bit extra here with this is not shown by default, but it's a really convenient little tool here that I may want to put here. This one here will now in a minute show us actually the FRF matrix and how things are looking. So I will try to now hurry up because I can see time is flying. I need to get started with my impact testing here. I will have to go to this little hammer setup I did up here, and now I can set up the sampling frequency I'm going to use. I can set up how long should the data segments I'm measuring be. I like to have 2048 samples. Then I can try to impact now on this structure here. Different locations just to see what is the level actually of input forces we have in this case here. And then we can see it down here. Let me just enlarge this one here. We can now see all the different impacts I made here. And this will allow us now to set up, say, the level of the hammer. So we do that here. And now the next we have to do is we have to go and set up if we need some windowing going on here. What I can do is I can always start setting up a force window for my inputs. You should always use a force window that will kill everything after the impact, and then it will die out to zero because there's no need to measure all that rubbish that you otherwise will get. So get rid of it by adding this force window here. Let's try and see if I make an impact now, how it looks. Here we have a nice free decay. It's not going all the way to zero as we can see here. I could try and make another one in the other direction here and see how that looks. Oh, that was a double hit. Yeah, then you can see really that this signal here is not dying out to zero here, which is not convenient. It has to do that in order not to get problems with our analysis. So we have to actually introduce a window here, exponential window on the response. And we do that here by choosing exponential here. And then choose here how much should this window actually reduce the response level to in the end. And we would like to go to, let's say, 5% in this case here. If I now show you here, I can actually show you now the window data here. And now you can see how it nicely goes to zero here with this window here. So I can actually put the raw and window. So here we can see the window and how the raw data is looking behind. So there are different options available, as you can see. Up here, we have now a force window. But since we now have added this exponential window in the response, remember that to produce the FRFs, we are dividing the response with the input excitation. So we should have the same type of window, exponential window on the top and the bottom, numerator and denominator. So when we divide it, basically the influence in the FRFs will disappear, at least on the height of the different peaks in the FRF will then be okay. So we have to introduce actually also a force and exponential window up here like this. Again, we can try look at how it looks here. This is now the exponential part looks like this, and then it goes down here and it kills everything in the rest of the signal here using the force window. This is what we need here now. We will stop it, and then we will say OK. And now we are ready to do the actual impacting. So I will get started. I just need to have a little bit more windows here to look at. You can see all these FRF entries here, they are all red. And as we proceed, we will see how they turn first from yellow and then to green. So I'll just sit down here now, and then I'll have to see where did I actually put the different sensors. You see the first one here is now located over here. So I will just turn this one a little bit like this, and then I will get started here and hope the best. And we can see here better like this, perhaps. So that will be this one here. Like this. Yeah. Oh, that will double it. Oops. Okay, and now we go to turn a little bit again here. So now I have to hit here on this part here. Ooh. Not easy. Yeah. Oops. Yeah. Okay, so now we have to go to the front of it. Yes. Let's see. All right, now I have to go here to the last. Like this. Ah. Oops, That looks ugly. We reject this one. Okay, try again. All right, that's it. Hopefully everything will succeed now. Just switch camera here again. So this is the test that has been made. Let's just save it. And now we can always go and we can check out how the different impacts are looking. Just by looking here at the managed measurements, here we can see everything that has been done. But what we now like to do is we like to switch actually and do some analysis. Just going back here to this presentation here, you can see we have two different ways of doing it. We have a peak picking tool that picks directly on the CMIF function, that is the singular value decomposition of the different FRF matrices. And then the other one that is the rational fraction polynomial that is fitting a series of different polynomials and then extracting the modes from this and presenting the information in a stabilization diagram. So there are these two ways of doing it. You can try and go to ARTeMIS and see how it works. Just remember that when we reach this this point here with where we are now in the prepare data task here and it has been completed, the software now has test geometry and it has FRFs available. So we are now at the same position, you could say, as we were in the two previous ways we did it, where we imported different types of data. But now we can go to estimation, and we have the two tools. We have the CMIF tool here. What we can do here is simply we can press this little button here, add new modes, and it allows us actually to go to the peaks, double click on them, and then immediately we can see, you know, modes shapes are looking like this over here. We can get them out here. Here we can see a nice mode that is moving actually in two different directions like this. So there are different modes available and we can simply pick them out like this. How many we now would like to have. It's a very nice, convenient tool to work with. The other tool is the more advanced RFP-Z tool. And if I go here and select this one here, I just need to select a setup here. Then I get this diagram here that is now empty. As we can see, up here we have a model order that can be controlled by this number here. So the maximum number 50 here can be set here. So that's a polynomial model order of this rational polynomial that can be put here. If we click this estimate models button here, you can actually see how we quickly can get many modes estimated with this tool here. We can also zoom in if we want. Let's say we only want to have some of these. It could be to here. So we only want this part here. Then we can just zoom like this, and now we can then get these estimated here, and then we get modes extracted over here that corresponds to this range here. So there are different tools available in the RFP-Z tool here, method here, where you can then define your own, you would say, range of frequencies that you want to find. And this is what is really nice with these segment methods. So this is how we can do this. We can then, of course, we can also animate modes and all this. There are other things that have been seen before here. There is actually seems to be a nice rigid body mode that we have very low down here. It is measured in the bottom, that's why it's not rotating, but otherwise that would probably rotate in the same manner as well. And otherwise we have some other nice ones as we can see here. And finally, the final thing we can do in the ARTeMIS Modal EMA is, of course, to compare what we have done. We can do that in validation. And inside here, all the modes that has been estimated by the different estimators, Also modes that you can import from another tool. That could be a fine element solver that you export modes from in universal file format, or other modal analysis software tools. You can actually import those into this list here also by clicking this button here and then import them. And they will then be lying in this list as well. But otherwise, it's a matter of comparing. You can select this one here and then similar one down here by pressing the control button while you are doing the clicking. And now you can actually see if we now try to animate these together here. You can now see how the two mode shapes look when you put them on top of each other for the two different methods. And of course, they should agree quite good. And it seems to be the case. There is a little bit of flickering because face issues are not, or faces are not completely the same. The blue seems to be the CMIF, yes, it's said here. And the red one is then the RFP-Z estimator. So this way we can now do comparison of the different modes that we have estimated, and that can help us to assess which of all these modes here that we should trust and which one should we either delete because it's maybe rubbish, or maybe go back and see if we can fine tune a little bit more with some of the settings of the different estimators. But this is ARTeMIS Modal EMA. Let me just wrap up here a little bit and say that it's an open platform you have seen today. ARTeMIS Modal in general is open. You can import from files from in different ways. We have many different file formats also available when it comes to time series measurements. I think we have more than 20 different file formats actually. So there's many different ways you can actually import data in and process it to get the frequency response functions. And you have also seen how we have done it directly inside ARTeMIS using some data acquisition hardware. I tried quickly to present different methods we have available. Some of the previous webinars, if you find those on YouTube, our YouTube channel, you can actually get more detailed information about the mathematics behind it. I chose not to do that today. And of course, then there is the validation that I just showed in the end. But this is actually what I wanted to show to you. If you want to have more information, then we have our YouTube channel, as I talked about. This presentation here, or this webinar here, will also be put there, and the ones that I talked about with try to show how to use or connect to the different hardware platforms that we support, they will come here in the next couple of weeks. So there are different videos available there, and also on our website there's many different papers, journal papers and other papers listing some of the mathematics that all the things in ARTeMIS is based on. So if you are into that, you can go to the literature page on our website, and you can actually probably have fun reading some of those. And of course, we have the software download, the trial version of our software. You can go there and you can try it out. You can then indicate if it's EMA, it's OMA, or SHM, or what is it that you would like to test out. And then we will try to send you a trial license for whatever fits the best. And next user training course I would like to mention also, this already in April next year, as usual I would say. And it means that you should already now consider if you want to go, then perhaps fill out the form we have on our website. There are limited space, limited seats, I would say. So make sure if you want to have a seat there to maybe list or join us already now on the website. Next webinar I will give is in December, on December 9, and that will be about operational modal analysis with ARTeMIS, of course. So I'd like to thank you for watching.